Okay, students. So right now we are discussing the topic of oxygen debt. What is oxygen debt? This is what we'll be discussing today, and I'll explain it to you with the help of a graph that I'm displaying to you on the screen. Okay, so the graph you can see here, it basically tells you how the oxygen uptake, which is displayed on the y-axis, varies when a person is engaged in physical activity. You can see the graph is divided into three segments: rest, exercise, and recovery. On the x-axis, you have time from 0 to 25 minutes. From 0 to 2 minutes, the individual is at rest. From 2 minutes to 6.5 minutes, the person was performing the physical activity, which is exercise. And eventually, after 6.5 minutes to 25th minute, the person was in recovery or post-exercise phase. You can see that initially from 0 to 2 minutes, the muscles of that individual were taking up oxygen at a constant rate of 0.2 dm³ per minute. This is called as the basal metabolic rate. The maximum amount of oxygen that muscles take during a resting condition. They are in a restful condition, they are not contracting actively. Whichever muscles are contracted, they are contracted to a certain extent. They are not actively respiring as much as they can, although they are contracted but not fully contracted anyhow. So then the person starts to perform a physical activity, which is, for example, an exercise at 2 minutes. You can see how the oxygen uptake gradually increases because the demand of producing ATP increases. So when additional ATPs need to be made, additional oxygen needs to be supplied to the muscles. But since the oxygen cannot be supplied right away when the demand increases, and yes, ATP needs to be provided to the muscles, what will happen? The muscles will start to produce ATP using anaerobic respiration simultaneously together with aerobic respiration, because oxygen is being delivered at a constant rate and gradually increasing, but ATP demand has increased. So additional ATPs are required, which are given by anaerobic respiration. Within 2.5 minutes, what actually happens, or within 2 minutes, heart and lungs, they bring about necessary changes to increase the blood pressure and the force of contraction of the heart. And the person starts to inhale and exhale deeply. So more oxygen is delivered to the actively respiring muscles which are engaged in the exercise now. So beyond fourth minute to fifth, sixth, and to 6.5 minutes, you can see the exercise continues and oxygen uptake is now at maximum 2.5. So during the time when additional ATPs were being made using anaerobic respiration, the person produced ATPs with oxygen deficit. So this is the oxygen deficit that built up, and this led to the buildup of lactate in the muscles, which caused muscle fatigue. Now with muscle fatigue in place, the person cannot continue exercise for very long. At 6.5 minutes of this graph, the individual stops exercising and goes in a recovery phase. Once he or she is in recovery, the muscle oxygen uptake start to decline. Post oxidized oxygen uptake is decreasing. You can see it's gradually decreasing. Eventually by 25th minute, it comes back to its original initial state of 0.2 dm³ per minute. Post exercise oxygen uptake is called as the oxygen debt. And why is this oxygen debt? This oxygen debt is required to pay back for the oxygen deficit. Oxygen deficit was the region when additional ATPs were being produced with anaerobic respiration together with aerobic respiration that was occurring in the muscles to provide those additional ATPs which were present or which were required for the muscle contraction, which was initiated due to engagement in physical activity or exercise. This oxygen that is then used to keep blood oxygenated. Plus, it is used for lactate removal from the muscle and taking the way lactate is taken to the liver and converted to carbon dioxide and water, as well as glycogen, as well as pyruvate. Carbon dioxide and water, as you know, it can be exhaled out. Pyruvate can be added into link reaction and Krebs cycle, and eventually into oxidative phosphorylation. So more ATPs can be made there. And if it is converted to glycogen, then glycogen can serve as a long-term energy storage molecule, having many carbon hydrogen bonds where energy is stored. Apart from this, increased metabolic state of organs after exercise also kept by this oxygen debt. So this is oxygen debt, and this is how anaerobic and aerobic respiration continues together. I give an example. I always give an example of this to the students, say that in exercise, for example, if you engage in weightlifting, if you are engaged in any kind of, for example, footwork or running or swimming, these are the exercises where you're contracting your muscles more than you contract them at rest. So initially your muscles are respiring aerobically, but when the demand increase, when you start to contract them more ATPs are actually needed there. So the muscles start to undergo anaerobic respiration together with aerobic respiration, and this is called endurance training, which occurs when you are lifting weights. Um, in comparison to aerobics or yoga, what happens there? The person just keeps the basal metabolic rate at certain condition that lactate is not built up. So that basically is aerobics or yoga. The breathing rate and the oxygen uptake is gradually increased in such a way with focus and with those exercises which they teach or which they practice, that the person's muscles do not go in anaerobic respiration at all. That's why it's called as yoga or aerobics. Okay. Then we can discuss the energy values of respiratory substrate. Energy density is the amount of density, or energy density is the amount of energy which is stored per unit mass of a respiratory substrate. There are three types of respiratory substrate: carbohydrate, lipids, and proteins. Carbohydrates have energy density of 15.8 kilojoule per gram. Lipids have 39.4 kilojoule per gram. Proteins have 17.0 kilojoule per gram. You should learn these values, and these should be quoted with appropriate units in your answer. Proteins are hardly used as energy density molecules or a respiratory substrate under normal circumstances in our body, but yes, carbohydrates are the main fuel for the body, and lipids are also used as respiratory substrates. Respiratory substrate just means the substrate that the body will respire to convert it into ATP and get energy from it. Now, what do? We need to compare the energy value of carbohydrate and lipid, and we see that carbohydrates have the lowest energy of all the three, and lipids have the highest energy of the three. So, why lipids have the highest energy? Because lipids have long hydrocarbon tails, and these long hydrocarbon tails have several hydrogens. So, these long hydrocarbon tails can be cut into two carbon units, which are acetyl, and this is carried out in mitochondria. And these two carbon units are acetyl units. They enter into Krebs cycle directly. So lipids end up producing more energy, because once these acetyl groups they enter in the Krebs cycle, there already will be oxaloacetate present in the matrix of mitochondria. So you can recall three reduced hydrogen carriers NAD are produced, and one reduced FAD is produced, and one ATP is produced right away in Krebs cycle in one turn. So you can imagine as many acetyl molecules are produced uh, from long hydrocarbon tails of fats, more reduced hydrogen carriers can be produced, and eventually each reduced NAD will end up producing 2.5 ATPs in oxidative phosphorylation, and each reduced FAD will end up producing 1.5 ATPs eventually in oxidative phosphorylation. Coming back. So, what is a calorimeter? Calorimeter is a device which is used to measure the calories of a for particular substrate. And how is it done? You use a device which is shown here in the figure. This device is filled with water. You note down the initial temperature using thermometer. You place a bell jar with a substrate which is 1 gram in mass in the in a dish here. There are two delivery tubes attached. One is the inlet for oxygen, one is the outlet for carbon dioxide and water, which are the waste gases. You note down the initial temperature using thermometer, and you ignite and you burn this substrate. For example, if this was 1 gram of carbohydrate, you burn it. When you burn it, it turns into carbon dioxide, water, and energy. Carbon dioxide and water go out through the exhaust, and energy is transferred to the surrounding water, which causes the temperature of the water to be raised. This raise in temperature is calculated, and with using the formula Q is equals to mc delta T, the energy density can be calculated for a particular respiratory substrate. We come to respiratory quotient. What is respiratory quotient, or RQ? It is the volume of oxygen used and carbon dioxide produced when a substrate is respired. Your formula is RQ is equal to CO2 upon O2. For aerobic respiration of glucose or lipids or proteins, these values have a straight values actually. So you need to learn these values. RQ value for carbohydrate is 1.0, for lipids is 0.7, and for proteins is 0.9. Aerobic respiration for glucose is this chemical equation, which is giving C6H12O6 plus 6O2 gives 6CO2 plus 6 water and energy. At times, these equations come for balancing, so you should know how to balance an equation of such sort. RQ will be CO2 upon O2, 6 upon 6. The answer will be RQ is equal to 1.0. So whenever the value of RQ is 1.0, it means that the respiratory substrate was a carbohydrate. Aerobic respiration of fatty acids, for example, C18H34O2, you can see how many hydrogens are there. There are quite a few hydrogens as compared to typical carbohydrate. You combine it with 25.5 oxygen molecules and 18 CO2 are produced 17 water and energy. You apply the formula of RQ CO2 upon O2, 18 divided by 25.5, and the RQ value comes out to be 0.7. 0.7 value is for lipids. So yes, lipids are being respired here. As I told you, proteins are hardly respired, so we can you can just learn this value. Normally, proteins are not respired in the normal circumstances. What about alcoholic fermentation? This is a type of anaerobic respiration in which carbon dioxide is produced in the product. C6H12O6 turns into two molecules of ethanol and two carbon dioxide and energy. RQ is equals to CO2 upon O2. Since two molecules of CO2 are produced, so this is 2 divided by 0. Why 0? Because oxygen is not used. This is anaerobic respiration. So you divide 2 by 0, the RQ value turns out to be infinite. What is infinite? Infinite means a very large value. And since our range of values are from 0.7 to 1.0, our infinite value will be any value greater than 1.0. Yeast respire anaerobically, but slightly aerobic respiration occurs too. So small volume of oxygen is taken up as well. So for yeast, RQ value is less than infinity, which means not a very large value. It is less than infinity, but it will be greater than 1.0 because 1.0 means carbohydrate are being respired. Greater than 1.0 means anaerobic respiration is occurring through alcoholic fermentation. So whenever you have a high RQ value higher than 1.0, it simply means alcoholic fermentation is occurring, or you can say anaerobic respiration through alcoholic fermentation, or and never the lactate pathway. Why never the lactate pathway? Because LQ cannot be calculated for anaerobic respiration occurring in muscles because that's the lactate pathway. You may recall in lactate pathway, neither carbon dioxide is produced nor oxygen is used. So if you apply the formula of RQ is equal to CO2 upon O2, that will be 0 upon 0, and the answer would again be a mathematical error. So you won't get an answer there because it's all zeros. So RQ cannot be calculated for muscle because for that reason. So the overall summary is that for aerobic respiration, RQ is in the range of 0.7 and 1.0. For alcoholic fermentation, which is anaerobic respiration, RQ will be greater than 1.0. This is all about RQ and oxygen debt and how a calorimeter is used. Thank you.